Alright, so in this video we're going to talk about sample surveys, and we're also going to talk about bias. Alright, so some vocabulary. A population is all the experimental units that you want to make a conclusion about. The sampling frame is the list of individuals from whom the sample is drawn. Not always the population of interest, so it could be just from a phone book, a list of registered voters, from the school roster. It doesn't always have to be specific to one population that you're interested in. It might be like everybody, and then that's where you're getting all your samples from. A sample is a small group of the population that you use in your experiment or your study or your survey, whatever you're conducting. A parameter describes a population. So the parameter, it's often unknown and it's often a fixed value. A statistic describes a sample of the population. This changes from sample to sample when we use statistics from repeated samples to estimate the value of a parameter. So a parameter is describing the actual population, and the statistic is a sample of the population. So it just describes that one sample of the population. All right, so some of the symbols we use if we're talking about the parameters, which is the actual value of the population. We have the mean is mu, the standard deviation is sigma, the proportion we'll call p. And then for our statistic, if our sample mean is x bar, our sample standard deviation is s of x, and our proportion we'll say is p hat. Okay. A sample is said to be representative or unbiased if the statistic accurately reflects the population parameter. Alright, example 1. A polling agency takes a sample of 1,500 American citizens from a list of tax returns and asks them if they are lactose intolerant. 12% say yes. This is interesting since it has been shown that 15% of the population is lactose intolerant. So 12% is coming from our statistic, from the sample. 15% is our parameter. It's coming from the actual population. Okay. The population is all American citizens. The sampling frame was the list of tax returns. My sample was 1,500 American citizens. And then if you want to include the parameter of interest, was the percent of American citizens that are lactose intolerant. Example 2. A random sample of 1,000 people who signed a card saying they intended to quit smoking were contacted a year after they signed the card. It turned out that 210, 21% of the sampled individuals, had not smoked over the past 6 months. So 21% is the statistic. So 21% of the sampled individuals. So it's coming from the sample, so it's the statistic value, not the parameter value. The population is all smokers. My sampling frame was people who signed a card saying they intended to quit smoking. That's where I got this information from. My sample was 1,000 people who signed the card. And my parameter of interest was the percent of people who have not smoked over the past 6 months, or the percent of people who had quit smoking. Example 3. On Tuesday, the bottles of tomato ketchup filled in a plant were supposed to contain an average of 14 ounces of ketchup. Quality control inspectors sampled 50 bottles at random from the day's production. The bottles contained an average of 13.8 ounces of ketchup. So 14 is our parameter. That's what they should contain. That's what the population should have. And the statistic from the samples we pulled was 13.8. All right, my population is all ketchup bottles. My sampling frame was ketchup bottles from 1 day's production. My sample was 50 bottles. And my parameter was the average number of ounces of ketchup in the bottles. All right, example 4. A researcher wants to find out which of the two pain relievers works better. He takes 100 volunteers and randomly gives half of them medicine 1 and the other half medicine 2. 17% of the people taking medicine 1 report improvement in their pain, and 20% of the people taking medicine 2 report improvement in their pain. So both 17% and 20% both come from the sampled people. So they're both statistics. The population is all people. My sampling frame was all volunteers. And then the sample was 100 volunteers, 50 taking medicine 1, and 50 taking medicine 2. My parameter of interest that I was looking at was the percent of people who showed improvement in their pain. All right, bias versus variability. Bias is consistent, repeated measurements that are not close to the population parameter. Variability, basically like reliability, consistent measurements. Doesn't matter if they're accurate or not, just are they consistent? Are they always in about the same spot? So to reduce bias, we randomize. To reduce variability, we use a larger sample. All right, sampling variability. Different samples give different results. Different size samples give us different results. And the bigger the sample, the better the results. Okay? So sampling distribution. If we take lots of samples of the same size and make a histogram, so we have a sample size of 100 and then a sample size of 1,000. So you can see the difference there. The larger the sample yields smaller variability. So how spread out everything is. Okay? We want it to be less spread, the better. All right, so let's look at these. I mean, you can see the arrow pointing to where the true parameter is. So the actual population mean. And then you can see the histogram of all the different samples. So the histogram, all the bars are all different samples. Okay, so in this one, I have a high bias because my actual true parameter is very far to the left. And I have a low variability. It's not that spread. Okay. In this one, I have a low bias. My true parameter is pretty much where I would expect it to be, in the center there. But I have a very high variability. It's a lot more spread out, the values. All the samples are more spread. The next one, it's very spread, and the true parameter is very far, so it has a high bias and a high variability. And then the next one, it has a low bias and a low variability. So that's what we're trying to achieve when we're setting up experiments or surveys or studies. We want to have low bias and low variability. So we want to have a large amount of samples, and we want to make sure that we randomize. Randomize to reduce bias. All right, so this is just another way of looking at it. Instead of histograms, if we had targets, okay, in the center being where we want to hit. Okay, so this one has a high bias. It's very far from my target, but a very low variability. Everything was kind of close, all in one small section. So bias is like accuracy, and variability is like precision or reliability. Okay, and this other one, I have a low bias. It's kind of close to the target, but high variability. It's very spread out. And then here I have high bias, high variability, low bias, low variability. All right, sampling designs. A good sampling design would be a simple random sample, or SRS. Every experimental unit has the same chance of being picked for the sample, and every possible sample has the same chance of being picked. Okay, so we would give every subject in the population a number. We'd use a table of random digits or a random number generator of some sort, and we would read across to select the numbers that would be in your sample, and we'd ignore any repeats. All right, so here are some examples. Let's take a simple random sample of 5, the following list. So I would take all those names there and I would number them. And then I would look at a table of random digits, pick a row, read across, and pick the first 5 numbers. Those would be the 5 people in my sample. Okay. The other one, take a simple random sample of the 4 of the following list of math teachers, so I number them. And then I could use a random number generator on my calculator. So math, probability, random integer, no repeats, from 1 to 18. And then the first 4 numbers that come up would correspond to the 4 teachers that I would choose. And we'll actually look at picking some of those in class. All right, so a stratified random sample is not SRS, so don't put SRS if it's a stratified random sample. SRS is just for simple random sample. So we would divide the population into groups with something in common called strata. So maybe it's by their size, by their gender, by their age, whatever. So something that they all have in common. And then we'd take a simple random sample, take separate simple random samples for each strata and combine these to make a full sample. Okay, so it can be sometimes a % of each strata. An example, we want to take an accurate sample of Sun Lake High School students. There are 50 freshmen, 425 sophomores, 485 juniors, and 430 seniors. Take a stratified sample. So I would break them into their groups by grade level. So those would be my strata, their grade level. And then I would take a simple random sample of freshmen, a simple random sample of sophomores, a simple random sample of juniors, and a simple random sample of seniors. And then sort of combine them somehow, maybe the average, whatever. Okay. A systematic random sample. The first experimental unit is selected at random, and each additional experimental unit is selected at a predetermined interval. So surveying every 5th person that comes into the door. So I'm going to start with the first person, and then every 5th person I'm going to survey them, or I'm going to do the experiment on them. Something like that. There's some method to it. A cluster sample, population is broken down into groups. All members of one group or more groups are taken as the sample. So you're only picking like one group. So we would break Sun Lake High School students into groups by class, freshmen, sophomores, juniors, seniors. And then I would sample all the members in one of those grade levels. So I would just choose to sample only the seniors. And I'm going to look at that cluster. And I'm going to use that to make my predictions or whatever. Multistage sample I would use for large populations. So an example, sampling the population in the United States, we might pick 50 counties, then pick 1 zip code for each county, then pick 2 streets for each zip code, then pick 3 houses per street, and go to those houses and survey them or do the experiment on them. Okay, this would be for a very large, and you wanted to get more randomized. So multi-stage has multi-parts to picking these samples. All right, bias sampling methods. Voluntary response sample chooses itself by responding to a general appeal. So call in, write in. Their response is voluntary. So they're going to choose if they want to participate or not. Convenience sampling. So selecting individuals that are easiest to reach or contact. So these are biased ways of collecting samples. Okay, so convenient sampling, like, oh, I'm just going to ask my friends because that's pretty convenient for me. I can get a sample from that. But there might be some bias there. They might have all like-minded as you are, and they might choose something that is not true to the population. Under coverage, sampling in a way that leaves out a certain portion of the population that should be in your sample. So telephone poles, maybe not everybody has a phone, or maybe they're only looking at numbers out of a phone book and doesn't include cell phone numbers. Registered voters, well, a lot of people aren't registered to vote. Stuff like that, where it leaves out a certain portion of the population. Non-response bias is introduced when a large amount of those sampled do not respond. So you were selected, but you didn't respond back. So you don't answer the phone, or you hang up when they call for a survey, or you don't mail back the questionnaire, or you just refuse to give an answer. So that's non-response bias, and that will change how we look at the entire population if that's what we have going on. Response bias is anything in the survey design that influences the response. So respondents lying, responses to try to please the interviewer. So sometimes if, depending on who's asking the questions, your answer might be different to kind of impress them or not be judged harshly by them. Unwillingness to reveal personal facts or information, like if they asked your weight, maybe you don't want to tell the truth. Leading or confusing questions. So sometimes they'll word the question in a way that kind of leads you to choose one answer over the other. And then voluntary response bias. Some people are eager to volunteer when they have a strong opinion on the matter. So it might be biased just by the people that have a strong opinion one way or the other. And those are the only people that are responding because it's completely voluntary.